Good evening, everyone, and thank you for listening to the Futurati Podcast, where we dive into how emerging technologies will impact the world and your bank account. I'm Trent Fowler, and today I am bringing you a solo interview because my co-host Thomas Fry is in Korea doing something amazing and awesome, I'm sure. But Thomas and I are futurists, keynote speakers, and consultants with decades of experience in analyzing new trends and communicating new developments to audiences across the world. Reach out to us at futuratipodcast.com/contact-futurati if you'd like to hire us for consulting, to speak at your event, or to advertise on our podcast. I just wrapped up a remarkable interview with Nick Frosst, who is one of the co-founders of Cohere, one of the larger generative AI platforms in the world. And he also has a background in cognitive psychology. So he's a computer scientist, a cognitive scientist, and also a musician who's running a major generative AI platform. So he's got a really wide-ranging and deep perspective on this technology, its potential, its the ways in which it will be dangerous or not. And so it was a real pleasure talking to them. We spent a lot of time discussing the nuts and bolts of transformers, the basic constituent parts that go into large language models. We talked about what it is that LLMs and image models are doing, the ways in which that is very different from what human beings are doing, and the reasons why Nick is very skeptical that deep learning will ever scale up to artificial general intelligence or become dangerous in the ways that many people are concerned about. So this is part of an ongoing series we're doing on the philosophy of artificial intelligence. We have done a number of recent interviews with luminaries in fields like epistemology, philosophy, computer science, and entrepreneurship, talking about these technologies. So definitely check out this interview, check out those others, and drop us a line if you find any of this interesting. So without further ado, here's my chat with Nick Frosst. Nick, thanks so much for coming on the show.
Yeah, thanks for having me, man.
Let's hear a little bit about your background, your interests, and what brought you working on the projects that you're working on today.
Yeah. So I have an undergrad in computer science and cognitive science. I think I've always been interested in AI stuff. So when I went to school at University of Toronto, I went to computer science to study that, and then discovered cognitive science shortly after getting there. Out of school, I started working at Google for a little bit, where I was working on neural nets as a production engineer, and then shortly after that switched into a research role in Google Brain, where I worked with Geoffrey Hinton on a bunch of different research stuff. Most of it was not involved, most of it was not related to language, but I met Aidan Gomez, the CEO and co-founder of Cohere, and he was super excited about transformers, and talking to him made me really excited about it. And then we started Cohere in end of 2019, 2020. And we've been working on language models since then.
You guys were pretty early in seeing the potential of transformers, I gather.
Yeah. I mean, he certainly was. He was working on that paper in 2017. But it wasn't until a few years later that we were like, oh wow, these are going to keep scaling up. So yeah, at the time it felt almost a little late.
Really? Well, that's fascinating. Do you have any thoughts as to why the transformer architecture under the hood is so good at capturing long-range statistical dependencies of the sort you see in images and videos? I think that took a lot of people by surprise, and to the best of my knowledge, it's still not really clear why that structure did so much better than ReLU or some other activation function or some other way of setting it up under the hood.
Yeah, I have some intuitions on that. First of all, ReLU is a non-linearity, and the thing is you can use a ReLU in a transformer. The specific thing of a transformer is the key value matching, because you have a thing that splits your activations into three, and then you're looking for similarity between the keys and the queries, and then based on that similarity, looking at the activations of the keys, queries, values. Wow, it's been such a long time since I've actually thought about the inner workings of a transformer. It's so funny. At this stage, it's just it's not really relevant. It hasn't changed in a while. It's just been consistent. And so I haven't I remember one of the Cohere initial interviews that we used to give people was to get them to implement a transformer. And
Did you do that now?
Yeah, it's been such a long time since I've given that interview. Would I even get it right? I don't know. Anyways, Yeah, I think there's two like things that work particularly well in transformers. One of them is not very contentious, which is just that the underlying math that needs to get done for a transformer network is easy to scale on a GPU. That's one. So like it just so happens that you can make really, really big transformers easier than you can make really big versions of other sequence models. So you can make really big transformers easier than you can make like big LSTMs. It's just easier to scale them up. So when I was working with Geoff Hinton, we worked on an image recognition model called a Capsule network.
Yeah.
And this was very good at image recognition, image classification, but very, very difficult to scale up. So if you tried to make really big capsule networks, like they had these weird inner loop things, they used a whole bunch of memory. It was just like really difficult to make big versions. And so we never even trained one on like ImageNet. We trained them on CFAR10 and ImageNet, or maybe we did train them on ImageNet eventually, but we never trained them on any like real world production data set because scaling them up was so difficult. And that was a function just of the architecture itself. So transformers just happen to have an architecture that's particularly easy to scale. And that's like one reason why they're great. It's reasonable to train, 100 billion parameter transformer model in a way it was not reasonable to train 100 billion parameter other forms of models. So like that's one thing. The other thing that I think is good about transformers, and this one is like a little contentious, like this, like some people, like I've talked to some people about this and they disagree with me. So I might be really wrong about this one. But when I look at the transformer, I think one of the things it does really well is looking for agreement between learned representations as opposed to just template matching. So a regular neuron in a neural net, it has a weight matrix and it's multiplying that weight matrix by an activation. And it's kind of just saying, does this activation match this template? That's it. It's just saying like, okay, like the activations I got on this layer, when I multiply them by these weights, do I get a big number or a small number? That's it. So there's really only one way for a neuron in a regular neural net to be active. It's either active or not active, and it can be more active or less active, but it's active in the same way. It's just like this sublayer activation pattern matches my weights. Great. That's it. In both a capsule network and a transformer network, you can have like, oh, well, you have 3 different representations that are each learned. And we're looking, hey, does this representation that is learned match this other representation that is also an activation? And if so, we'll be active in this way. But like, if you have changes in the activation, as long as they're changed in a way that agrees, you can still be active. So a capsule network does this really explicitly. A capsule network is like looking for agreement in learned representation. So like a capsule in a capsule network can be active in many different ways, as long as the representations in the level beneath agree. A transformer is doing like a simpler version of that, in which you have your learned activations in like in your queries and your keys, and you're seeing if they match. So to me, like the transformer, like the reason why I got excited about it is when Aidan first explained it to me, I was like, wow, that looks like the good stuff of capsule networks, but in a way that is really easy to scale.
I see.
I've had this argument when I've had this argument with people, and they've been like, nah, that doesn't, I don't really think that. So I don't hold this opinion too strongly. But when I have to explain why the hell is a transformer so good, why is it so much better than other things, I think it's somewhere in those two facts.
Well, it's fascinating. I want to come back to scaling because obviously that's very important in the current discourse around AGI and AI safety. But I'm curious, I want to drill in a little bit more on this learned representation thing. Or are you talking about the statistical function that it learns over its data set, like the representation of the statistical patterns in the language corpus it's trained on, or the image corpus that it's trained on? Like you say learned representation, can you tell me a little bit more about that?
Yeah, I mean that's the way all neural nets work, right? Like we start off with a totally random neural net. Mm-hmm. You give it some input, and every representation is just a random projection of that data. So if you're giving it like an image, you look at the activations on the second layer, and it's just a random thing based on the stuff you gave it. In a language model, you give it a bunch of tokens, and then we learn some random activation based on the tokens that you gave it. So it's the same thing. It's just through gradient descent that we like learn a representation that is useful for downstream classification.
Okay. And so you said that a transformer is good at finding an agreement between different learned representations. Is that right?
Yeah.
So in what sense is there more than one? In what sense is there more than one if the learned representation is just captured by the internal weights in the structure of the linkages of the network?
Yeah. So in a capsule network, the activation function is looking for like it. So we're going to activate this. I haven't talked about this stuff in so long.
Curveball.
It's literally been like years, because in some ways we just don't think about it anymore. Now we think about the data, we think about like latency, we don't spend a ton of time thinking about the architectures themselves. Anyway, I certainly haven't thought about capsule networks in a very long time, but I do think they're relevant here. So in a capsule network, like let's imagine two different image recognition networks. One is a convolutional neural net, and one is a capsule neural net. Our convolutional neural net, for any neuron, it has this weight matrix, which we're gonna do a convolution on. So we're gonna apply it in a bunch of different places on the image, and if any of those places get a high activation, we're gonna have a high activation for that neuron. So imagine we have like an eye detector, like a little thing that if ever it sees something that's roughly the shape of an eye, it's going to be active. In a convolutional neural net, we do that at a whole bunch of different positions in the image. And if there's an eye anywhere in there, that eye neuron's going to be active. But there's only one way for it to be active. It's just either active or not active. And it can be, regardless of where the eye is, it's either active or not active.
Like a real neuron.
It's just like there's an eye somewhere in the image. That's the thing. In a capsule network, we don't just have like we're not just matching a thing and seeing, hey, does this little convolution fit in any one place in the image? Instead, we're going to have a feature that's going to be active, and it's going to say there's an eye, and there's an eye in this way. So its activation is not just a single number, it's a little vector. And that vector, or it's a matrix, so there's multiple different ways of formatting it, but it's a little thing that says there's an eye, and it's kind of like this. And you can say it's an eye, it's an eye and it's big and it's pointing to the left maybe, or it's an eye and it's like kind of a human looking eye, or you can have more information in the way in which it's active. And then when we look at higher level features in the convolutional version, we'd have like, is there a human face there? Well, is there an eye capsule? Is there an eye neuron that's active? Is there a mouth neuron that's active? Is there a nose neuron that's active? If so, like, yeah, there's probably a face there. In a capsule net, we have, is there an eye kind of at this location pointing this way, and a nose at this location that would also tell you pointing this way, like that it's in the right location? Is there a mouth in this location that's like, are they all agreeing? Are they making a prediction for a face in a way that agrees with each other, or are they making completely different versions?
Hello, this is Trent Fowler, co-host of the Futurati podcast. One of the most common pieces of marketing advice I've come across is to know your audience and give them what they want. One difficulty in podcasting is that it's actually pretty hard to do this. None of the major platforms give us any way to reach out to you, our listeners, to find out what you enjoy about the Futurati podcast and what you'd like to see done differently. So we've decided to record this commercial and ask you directly to reach out to us. Head over to futuratipodcast.com, go to the contact page, and drop us a line. Tell us about your favorite and least favorite episodes, what you'd like to see us cover in the future, and anything else you want us to know. We produce this show for you, and we want your advice so we can make it even better. Thank you.
I see. Okay. So the activation pattern contains a lot more information, and there's like subtle relationships that it can catch by looking at the agreement between the different representations.
Yeah. And now a transformer, I think, is doing something kind of similar. I think in the three-way learned representations, instead of a thing just, instead of we're having a single activation vector multiplied by the weights, and we look at how large that is, we look to see, is there agreement between the key representation, the query representation? And if there is, we multiply that by the value representation. And so that's a way of each neuron within a transformer being active in multiple ways. At least I think it's very hand-wavy. And when I have brought this to people, they've been like, nah, I don't really think so. I think it's just about the scaling. And I think that's I think that totally might be it. I think it really might just be the scaling. But if I had to be like, is there something beyond the scaling? I'd be like, well, maybe it's this.
Something special about that. Well, that's important too, because, we have been surprised at the sorts of speed ups that you can get by just switching out, like, what was it, softmax with ReLU, I think. And then when they introduced transformers as well, you were able to just get these networks. They were able to do substantially more powerful things. Well, and it wasn't really clear in advance why that would be the case.
Yeah. Well, I mean, ReLU and softmax are two very different nonlinearities. Is there ever a time where you could swap out one for the other? I don't know. I think people have occasionally been like, surprised at the efficiencies they get from making small changes to architecture. I would say there's probably people who are a lot smarter than me who aren't surprised by those efficiencies because they understand the way GPUs work and they understand how you can speed up things by making kernel changes and stuff like that. That's never been something I've been good at. So I think there are some people who are not surprised at the speed ups they get when changing architecture. I know that when I was working on Capsule networks, I was surprised at how terrible they were when speeding up, when trying to scale them up, and how inefficient it was. And that's because I didn't really have a good low-level understanding of GPUs. Yeah.
I see. Yeah, I really don't either. I used to be a machine learning engineer, but I definitely didn't have a granular understanding of how the underlying hardware was going to impact things like that as the systems got bigger. I'm curious as to what you think about the scaling hypothesis more generally. So a lot of the power of transformers came from the fact that they're just much easier to scale than an LSTM or an alternative architecture. Do you think that we're going to start seeing diminishing returns to just building deeper networks over time, or is there a lot more juice to be squeezed out of this approach?
It depends what you mean by diminishing returns. I think we can make transformers that are a lot better than they are today. I think we can keep making language models, sequence models that are much better at predicting the next token in their data set and that generalize better and that are easier to use by making bigger and better transformer-based language models. I think that's true. Do I think we're going to get to AGI by just training bigger language models? No.
Why is that? That's an excellent segue into my next question.
Yeah. Because I think when we talk about AGI, really what people are often talking about is like human level intelligence. Mm-hmm. I mean, like, can we make a thing that's as smart and not only as smart in the same way as a person is smart? And you are doing something very different than language models are doing. And as a result, you can already see the divergence, like the types of things that trick up language models do not trick up people. And there are things that people get tricked up on that language models find very easy. Like language models are really great at some things that people are very bad at and vice versa. So they're very different. That should not surprise anybody. The way we train large language models is very different than the way you are trained, than the way you learn. There was a very similar thing that happened when image recognition was the big thing. People were like, oh man, we've solved image recognition. We have computers that are better than people at image classification when we had convolutional neural nets. And that's not true. We don't have computers that are better at vision than people. We have computers that are better at predicting, given some training data set, which image belongs to which class. We have that. But we don't have computers that are better at vision as like a general ability. We have them that are better in a particular thing. That's kind of similar with language models now. We have language models that are really great at modeling some forms of language that people find challenging, but we don't have models that are you can use words the way humans can use words. So I think when you, look at the history of how neural nets have, what they've been great at, what they've been bad at, you should feel like, hey, we've kind of been here before. It's just that now we're doing it in language, which feels like it's a lot broader, which feels like it's a lot closer to intelligence itself. But it's not. It's a restricted component of it. And we might excel at that component, but that's not going to give us intelligence itself.
Well, what is intelligence itself? Because I find that a lot of intuitions are powered by differing definitions, which are often implicit, of key terms like agency, consciousness, or intelligence. So you worked in cognitive psychology. Surely you have like a carefully worked out intelligence definition you can just rattle off right now on the spot.
No. Yeah, no, I don't. I don't. Yeah. So that's why when I talk about it, I don't like to talk about AGI. I like to talk about human level intelligence. And I really want to define that based on behavior. Like, we're going to have human level intelligence when you treat a language model the way you treat a person. When you expect them to behave and do all the things a person could do. And we're not close to there. There's lots of things that you would rely on a language model to do something very differently than a person would do it.
Like what?
So language models right now, there's even low level things. Like, a language model is at this stage often much better at writing a summary of an article than a person would. They can do it way faster, and they can do it almost immediately, and I could give it very specific style requests, and it can handle that job very well. But if I give it some, textual description of an environment and ask it to make some planning steps based on, the way that environment unfolds, it's going to get it wrong. A great example of this is you can take any brain teaser and change the brain teaser a tiny little bit, and the model will almost certainly always get it wrong. And I don't think more training and more parameters is going to fix that problem. Because when you look at the loss function, it's not often rewarded for understanding those things. It's trained on predicting the most likely next word, and the most likely next word is not often based off of a deep understanding of the way the world works. It's based off statistical correlations in text.
Right, which is very different than an agent like URI is doing.
Yeah.
But I'm curious, you said the loss function, it's not being rewarded for understanding things. I agree. Could it be, though? I know there's causal artificial intelligence. There are a couple of other approaches to building causal understanding into these systems. I don't know. I haven't looked into it in a while. I don't think it's gotten that far, but could you train an agent to do that? Because I know that they're trying to put LLMs in robots now, and they're building these multimodal models that are gargantuan and quite powerful in various ways. I think an Eliezer Yudkowsky would say, well, the process of training a neural network doesn't look so different from natural selection. And we've repeatedly been surprised at how just stacking up more layers has gotten us dramatically more functionality in a way that many people would not have predicted in advance. So I think he would say that you can't really rule out the possibility of a general mechanism falling out of that, because that's what happened the first time that humans evolved.
Yeah, I think that's pretty off base. Yeah, I don't think gradient descent is a lot like natural selection. I also don't think when people say we've been surprised, I don't think it's been that surprising. I think when you look at Transformers in 2019, I'm yeah, where we got to now is about where I would expect us to get. I think there have been times when I've been surprised at how good neural nets are, but mostly I've been surprised at being wow, they're actually more data efficient than I thought they were. Actually, you can fine tune on a relatively small data set and get some pretty cool behavior out of a transformer. That's a surprise. But yeah, no, I think it kind of made sense when you saw the very first transformer. Making them much bigger and training on much more data was going to get to where we were going to get to now. I think the idea of doing next word token prediction and gradient updates based on that, somehow getting emergent human level world intelligence out of it, I don't see how we could get there at all. And I don't see any indication that we are getting there. I see we're getting much, much better at next token prediction, and I think that that's incredibly powerful. I think next token prediction is it is crazy. It's one of the most useful things we've made a computer to do, and I think they can still add so much more value just doing that. But I don't see how next token prediction gets us to intelligence like you and me. And when you think of how we behave, here's a really great example. A few years ago, there was a Google paper that came out that showed models that learn A is necessary and equivalent to B. They do not, if they have a bunch of those examples in their training data set, they do not learn that B is necessary and equivalent to A. So if you say like, A equals B, they do not learn that B equals A.
See.
And when you think about the training loss, that's not surprising. There's not many examples in documents where someone says A is equal to B, and by the way, B is equal to A. That doesn't happen very often. And so there's very little gradient that should tell you if A is equal to B, B is equal to A. You just learn A is equal to B, because people don't run around saying, this is my father and I'm his son. They don't run around saying, like, this, I live here and here is where I live. They just say one of those things. So you don't get this, like, you don't learn these like logical things. Whereas you and I were constantly getting updates based on reciprocal relationships. Like if I am sitting at a table and I know that the glass is on the table, but I forget that that means that the table is beneath the glass, I'm going to knock over the glass. If I forget these relationships because I only think of one direction or something, I will, run into walls. So we get a lot more updates on that.
Yeah, we don't think to say those things because it's just, a human wouldn't think to specify that, right? Like if A equals B equals A, that symmetry is implied. You don't need to spell it out.
Yeah, and
also, with context.
Yeah, and we didn't learn that through language. We learned that through walking around the world.
Okay. You said earlier that next token prediction is one of the most powerful things we've gotten a computer to do, and there's still a lot of room for it to add more value. Talk to me a little bit about that. What do you see as the most valuable use cases out of something like this, especially in view of the fact that it's prone to hallucinations, has no truth model, et cetera, et cetera? Like what are the major things going to be major use cases?
Yeah, well, I mean, the truth model thing is, I think, a severe limitation, but that can be circumvented by using retrieval augmented generation. So there's many limitations of language models, but we can also often get around them by using a language model to learn how to use some external tool that solves it. So like a great example is like language models are bad at math. Not surprising. They're trained on next token prediction, and trying to memorize all the math equations is a bad way of learning math. But you can train a model to write mathematical equations and use a coding language or a calculator to calculate those, and then get the model to answer a question based on that external source of mathematical calculation. So we run into problems with language models like, oh, they're not amazing at this, but we can often fix them by using a language model itself to learn how to use a tool to fix that problem. And when I say there's so much more value they can add, I mean, like, I still do a whole bunch of work in my life that is effectively, taking a document and changing it into another document, or, reading this long thing and extracting the key bits, or, I often do work that is look at text and solve some other text problem based on it. And like a language model should be doing all of that. Like that's, I think at some point we'll get into a thing where you will come into work, you'll open up Slack to talk to people, and you'll open up a chat model, and like a huge amount of your work will be asking the chat model to do things. To be like, read these documents and write a brief. Okay, turn that into a slideshow. Okay, email it to this person. Okay, make a tweak like this. Actually, this is slightly better. Okay, cool, I'm done. There's gonna be huge amounts of work that is just like offloaded onto this massively powerful sequence prediction model.
Well, a fair bit of that you can do now. So what do you think's missing from that recipe? I mean, I do some of the writing tweets or summarizing this transcript. I'll probably do with AI. So is it agents? Is agents like the next step?
So, I mean, you do it, but you're also hosting a podcast and work at a large language model company, right? Like it hasn't gotten everywhere because there's barriers to entry. A lot of the barriers to entry are like not understanding how it works, but also really simple things like it's not integrated into your documents, or like it's not hosted in your environment, or it's too expensive. Like there's all kinds of things that are not AGI problems that are just like development problems that prevent people from using this.
Okay. And you think like, what's your prediction for how quickly we're able to overcome those hurdles if you have one?
I think pretty quickly. Yeah, I think pretty quickly.
Yeah. So we're not too far away from a language model being almost like a pencil or a calculator. It's just like it's on the desk when you get there.
Yeah, I don't think we're too far away from a bunch of people relying on it for their work. Yeah.
Are you at all worried about technological unemployment as a result of that? Or do you think are you an optimist that thinks it's just going to supercharge everyone? And
no, I'm not really worried about that. I think there's still especially because I think, if you start with my premise of saying this is not AGI, there's still humans are, incredible at all kinds of things that language models are not incredible at. I think we should be having people do those things. And I think there's sufficient, I'm not worried about this displacing a ton of jobs, because I think really what this is going to do is speed up a bunch of them. Now, is that going to change the economy? Yeah, I think so. In the same way that lots of any technology has changed the economy. But do I think it's going to be massive, some, completely restructuring? No. In the same way that the internet changed all kinds of jobs. And yet fundamentally, the world today looks pretty similar to the world before the internet.
Are you enjoying this episode of the Futurati Podcast? If so, please like it, give the show a 5-star rating on Apple Podcasts, Spotify, or wherever you get your podcasts, and share it with your friends. By far, the best way to help us grow is to spread the word on social media, which will expose our content to more people and help us continue to bring you interviews with world-leading experts in AI, quantum computing, cryptocurrencies, and so much more. Thank you in advance.
Well, but I'm a technical writer, so if the models are good enough to just take a spec or an API and generate docs out of it, it's sort of hard for me to know what I'm going to be doing other than just talking to people on Slack and signing my name on the outputs.
No, I think I think we'll totally be able to use a spec and write docs, but will those docs be understood in the cultural context? Will they be presented in the right tone? Will you be able to validate them as a user? Will they highlight the particular things you want to highlight? Maybe not. That's something you'll still be working on.
You're like a translator from LLMs to normie?
No, I think it's more ultimately you have to remember that that the jobs and the economy exist to serve people, right? And we're going to make some things that people do a lot easier, but ultimately we do things because people need them and want them, and it's other people who want them, and so you'll be tailoring the output considering the people who you're working with and the people who are your customers.
Yeah, a thesis I advanced, 20 or 30 episodes ago was that we probably move more and more towards last mile creation or last mile work, where what you're doing is starting with a draft of a program or a code base or a blog post that was written by an LLM, and then what you do is tweak it from there and make sure it plays nicely with all the other systems and integrations, and basically just handle that last thing. And it's an analogy to last mile delivery, right? So for a long time now, people have worried that automated driving, autonomous vehicles was going to replace long haul trucking, but getting that last mile, the hard part is not driving 200 miles down the highway. The hard part is backing it into the bay at Walmart and unloading everything and not hitting a kid that's happens to be running across chasing a ball in the parking lots. I think more and more work will move into the long tails, but long tails are long and there's still kind of a lot to do.
Yeah, I think so. I don't want to downplay the importance of that last mile and language stuff. That's actually where a lot of the meat is. That's actually where a lot of the real hard work is.
Fascinating. Well, this is much more optimistic than most of the conversations we have about this subject, so I'm glad to hear all of that. I wanted to switch gears a little bit and talk about some of the cognitive psychology work that you've done in the past. So I know that you've done a lot of cog-sci research, and I'm just curious as to whether or not you have any thoughts on other approaches to artificial intelligence that might also be very powerful. So Gary Marcus is firmly in the neurosymbolic AI camp. I know some other people who are interested in causal AI and various other similar sorts of approaches. So is there anything you've encountered in doing all of that research that you think might be another piece of the puzzle that should be explored?
Well, I want to start by saying I haven't done a ton of research in it. I have an undergrad in cog-sci, and I did some studies with some professors here and worked with Geoff Hinton, but I am not going to claim a ton of, a huge pedigree on this. There's a lot of people who spent a lot more time thinking about it than I have. But are there other forms no. And by that I mean neural nets are the thing we've made that is the coolest. Neural nets, gradient descent, statistical models of data sets. are the thing we have done that seem to generalize in the way closest to people. And that makes them the most exciting and I think often the most useful. So the other forms of like, I guess there's some forms of AI that were like amazing that we don't think about anymore. Like, Monte Carlo search for chess was like really cool and figured out how to play a chess bot, beat everybody at chess. And like, that was amazing. But like, it's been long enough now that we just we don't think about that as AI anymore. We think about it just like, yeah, it's a thing a computer can do. Cool. It's not surprising. It doesn't cause us any philosophical angst. I think language models will get there at some point. They won't cause us any philosophical angst. They'll just be like, yeah, that's a thing a computer can do. You can train it on a whole bunch of statistics. It can update based on what it has learned in that, and then write very plausible, reasonable, useful stuff based on it. But it's not going to cause you philosophical angst. I don't think the other things, like the other approaches that I've seen over the years, they haven't gotten closer than neural nets have gotten. Now, I also don't think neural nets will get there. I think we'll need something completely different. I haven't seen it yet, and I don't know when we'll see it. I'm not like people who are running around saying like AGI in 2 years, or like, I don't think so. I don't know when we'll get there. I have no reason to think we won't at some point. I'm like, surely, why couldn't we build a mind out of a computer? I see no reason why we couldn't, but I haven't seen anything that would get us there. And I think we'll need a whole bunch of independent breakthroughs that will look very different than what we have today to get us there.
That's fascinating. So I know you don't want to spend too much time on this, and I don't either, but assuming that we did get to AGI, like a human-like mind in a computer, do you think that any of the safetyist concerns then become more plausible, like recursive self-improvement or misalignment or something like that? Or do you believe that a silicon-based mind built by human beings would somehow internalize many of the same values or be steerable in some way that's renders the whole terror around them mute?
So I think one hypothesis is that if we're going to build a human-like mind, it's going to be limited in the way a human-like mind is limited. Like that might be true. And if that's true, then yeah, there's not it's not like there's new fears. The worst is, the worst is a person with malicious actions. Like we already have that. We have lots of malicious people out there trying to do malicious things. We have a system that prevents them for the most part. So if it turns out that to build a human mind, it needs to be limited in the way a human mind is limited, then like, no, there's not something to worry about. If it turns out we can build something that is a human mind that isn't limited in the way a human mind is limited, that isn't mortal, that can be copied many times and still work together, that can, build itself and recursively improve or something, then yeah, there's something to be worried about. And like, that's an interesting philosophical conversation. I think it's much too early to have those philosophical conversations given where we are now. And I think the past 2 years of history have kind of already made this point, right? Like people started having the like doomerism stuff, the like, oh no, language models are gonna, destroy the world. Like they've been talking about that for years. And as we've seen language models get better, we have seen none of those fears come true. The fears that people have been thinking about are a lot, and like need to continue to fear about, are a lot lower level and a lot more like subtler, but in some ways more important, right? Like I do want people to talk about how the job market is going to change based on this. I do want people to talk about the, identity authentication on the internet and making sure we're not having a bunch of, mis and disinformation conversations with bots thinking they're people. Like I do want people to be thinking about these immediate real world risks. And I've been pretty optimistic over the last little bit, seeing governments swap away from talking about doomerism and like bioweapons and more into misalignment, disinformation, bias propagation, things like that.
Okay, fascinating. I wanted to spend a little bit of time talking about your interpretability work, specifically what you covered in your paper, Neural Additive Models, Interpretable Machine Learning with Neural Nets. At first, I thought that we could just cover what you covered in the abstract of that paper. That's why is interpretability so important in the first place? Why is this something that we should care about?
Well, I wrote that paper a while ago, but and I'm not even sure I was the second or third author, so I'm not even sure I wrote the abstract. But
Maybe a language model did it.
I don't remember. But if you ask me why is interpretability important, I would say, well, interpretability is not actually that important. Intervention is important. People don't actually so a neural net is completely interpretable. If you want to say, I gave you this input, why did I get this output? I can completely explain it. I can say, well, I did this matrix multiplication followed by this nonlinearity, followed by this matrix multiplication, then this nonlinearity, and this was the output. That's completely interpretable, right? Like you actually understand much, much more why a language model predicted one next word versus a person. We can just do all the math, and we could be same with image classification. Why did the image classification model give this classification based on this image? Well, here's the math we did, and that's the result we got. But that doesn't satisfy anybody, because they actually don't care about being able to understand what the model is doing or why it made this decision. They care about intervening and saying like, well, actually, you shouldn't have made this decision, and I'd like you to make this decision based on these information, or I want to bias you towards this, or I want you to do something else. So it's not just the explainability that's important. It's the intervention. And the neural additive models was a way of doing that. That was saying like, what if we have a multivariable prediction, and we're going to have a whole bunch of different inputs, and we want to be able to control the consequence of each of those inputs. Well, we're going to learn a little function for each one, and then we're going to add them all together. And that way, if you want to take one out or augment one or change one, you can do that. You can directly change the process that is happening when making a prediction. And that was something that was easy to do with them.
Do you need a dynamic and knowledgeable speaker for an event? Thomas Fry and me, Trent Fowler, are both seasoned keynote speakers, able to converse on a wide array of topics to audiences of all sizes and skill levels. Go to the contact page at futuraudiopodcast.com to book Thomas or myself today, and let us apply our years of experience in public speaking to make your event a smashing success.
Fascinating. So you can actually change the pattern of outputs with neural additive models?
So with a neural additive model, it's like, imagine we have, we're going to make some prediction based on a whole bunch of attributes of you or something. And we're going to make a prediction, like a Gray said, people are going to predict like a loan that you might be able to take based on attributes. And one of those is your age. And we might notice that, hey, actually, when we train the model on the data set, it says that like, we should give loans to people who are above 30 and not give loans to people who are below 30. And we can see if you train a regular neural net, figuring out that it's doing that is kind of difficult. But if you train a neural additive model on this, you're going to see you can make a little graph for each input variable, and you can show what the consequence of that input variable is on the prediction. So we could say, hey, when you're below 30, it says really negative, and when you're above 30, it says really positive or something. And then we could look at that and we could say, actually, we want to correct for that. We don't want to make the decision based on that attribute. So either we want to say, okay, raise them all up, or we want to take it out completely or something, but it allows you to intervene in the process more.
It kind of sounds like SHAP for neural networks. You familiar with SHAP?
No.
It's Shapley additive something or other, but it's like Lime a little bit, basically. And this is off the top of my head. I haven't done this in years, but basically you're able to take permutations of different input features and test different combinations of them and see how each one is sort of impacting the final one. So it sounds a little bit like SHAP for neural networks.
I think, okay, this is all stuff that happened 6 years ago. So you're stretching my memory. But yeah, I think it is kind of like that. The difference is that the thing we're learning for each variable is a little neural net itself. And so that means it can model arbitrary functions.
Well, that sounds like Lime for neural networks. So with Lime, you do something similar. You take one row of a data frame, you perturb the data by sampling in an input around it, or a distribution around it. Then you feed that to the black box model, get out perturbed outputs, and train like a linear model on that. So you train like a little local model that can tell you in this region kind of what it's doing.
Yeah, that sounds similar. Yeah.
It kind of seems like a huge deal if you're able to model it that well and also intervene in the outputs. I'm curious as to why I haven't heard about this, because I follow Neil Nanda and Chris Olah and some of the other interpretability people. Like, how is it that I've not heard about neural additive models if they're as good as you indicate?
They're particularly for like they're useful for data sets like where you have a bunch of discrete features about a particular thing. They're not like, it doesn't help you at all with images. It doesn't help you with language. And the stuff that like Chris Olah in interpretability is in like a neural. You could train a neural additive model on an image, and you'd have like a little variable for every pixel, and it would be terrible. It wouldn't help. and it would tell you,
8 billion functions.
Yeah, it wouldn't be helpful. So what they're working on now and interested in is language and images. Well, to begin with, it was images. Now it's language.
Okay, I see. So the domain appropriateness is different for the different approaches. Well, that's fascinating, though. I wonder if there's a way to move it over, maybe group them, similar distributions or something, develop constellations. I don't know. I'm ranting. Okay, so I know that you are the lead singer and guitarist. Is that right? Of Good Kid?
Singer.
Oh, I thought maybe it was Wikipedia. So somebody said you were a guitarist. Okay, so you're the lead singer of Good Kid. You guys recently went on tour. And I know that you also published a paper called Text Conditional Lyric Video Generation. And I'm curious as to whether or not you have used generative AI in the creative process, if you think there's a whole lot of potential there for that, if you're at all worried about copyright. There's a whole hornet's nest we can kick here.
Yeah. So again, also that was about a 6-year-old paper. I think what happened is you looked at all the papers and you realized I've been working at Cohere for 4 years, and so I haven't been writing papers. So all these papers are very old. Yeah, but that's because I'm much more focused on actually solving problems with neural nets these days and like making a viable, useful product than I am.
Gotcha. Yeah.
Right. But yeah, we made actually me and the drummer from Good Kid made a paper many years ago on like generating music videos based on taking lyrics and doing a latent space walk in a text to image model to like make cool little videos. But I guess like to your question, like I am a lyricist, like I write lyrics. And I get a lot of people ask me the question, like, do you use, Cohere's language model when writing lyrics? And the answer is like, no, I don't. And that's because I'm not interested in writing lyrics faster. I don't particularly want that process to be efficient. I want it to be personal. I want it to be emotional. I'm not interested in getting that emotion faster. I'm interested in sitting and thinking about it. I do sometimes, after writing lyrics, paste them into Cohere's models and say, hey, like, what do you think about those lyrics? Like, can you summarize the themes or something? Like, tell me about the imagery that's used. And then sometimes based on what I get from the model, I'll update my lyrics. Like if I write in a bunch of lyrics and I say, what do you think this is about? And it says something completely different than what I intended, I'll be like, oh, I've maybe missed the mark a little bit. Like maybe what I think is evident is not evident. And so I'll go back and I'll make it a little more clear. Or sometimes if I put in a bunch of lyrics and say, what do you think it's about? And it's like, this is about exactly this. Here's exactly what's happening. I might be like, wow, maybe I'm hitting it over the head a little too many times. Maybe I should make it a little more subtle or something. So I'll like change what I'm writing based on the feedback that I get from the model, but I don't ever get the model to write for me because I don't want efficiency out of the process of art creation.
Yeah, it's meant to be personal. It's meant to be the stamp of a mind or a soul like yours that people feel like they can communicate with or connect with through the medium of.
I mean, that's what I want out of art. I think there might be some people, like I've done some art with neural nets where I've been like, it's really cool that I can make 1 million versions of this. And that's been involved in the artistic process. I mean, like, it's cool to incorporate this. But for the lyrics I'm writing for Good Kid, each one of them is me trying to express something. And getting a model to write it for me doesn't help me express that.
Do you have any information on other people, other artists who might be using this? I'm just thinking of having it like a conversational partner. It's just like, being an emotion or a feeling, and it's like, how do you react to this?
I kind of use it as like something to bounce ideas off of occasionally.
A soundboard.
Yeah, and that's like helpful. I imagine I'll keep using it for that, but I don't use it for writing itself, and I don't really know anybody who does either. Because again, I don't know anybody who's trying to do it faster.
It was a Connect week. Somebody said that they were having pretty good luck putting in like guitar tablature and having it generate things like guitar music as a result of that. I thought that'd be a cool thing to do, is like train it on Polyphia or Good Kid or one of these bands and have it generate new stuff or exercises for you to master the original song or something. It just seems like there's a lot of
that could be helpful. Yeah, for sure. Yeah.
Maybe Connect Week 2025. We can play a song in the style of whoever, generated by Command R 3+ or whatever it is at that point.
Yeah.
Well, do you have any other final thoughts for the audience? Anything else you want to communicate?
No, man. I think this is thanks for having the time. This is enjoyable.
Absolutely. I appreciate it. I appreciate the optimism and your perspective as somebody who's actually in the trenches building these tools. It's been very informative, and I really appreciate it.
Great. Cool. Well, I'll see you later, man.
Where should people go to find you? I mean, you've got music, you got all this other stuff. Where should people go if they want to find you?
Oh, I mean, Spotify for Good Kid and the internet for Cohere.
For Cohere. And then nickfrost.com, I think, is your website with your 6-year papers. Where I found them all.
I haven't updated that in 6 years. So, yeah.
And the bird link, it 404s now. I was like, oh, I want to listen.
I haven't said it in a long time.
Okay, excellent. Well, thank you so much. Thank you again. Good luck with everything, and I'll see you around.
Cool. See you later. Thanks, man. Bye.